The universe is full of these huge, terrifyingly empty spaces. They're not just blank spots. They're colossal regions hundreds of millions of light years across, where galaxies almost refuse to gather. And these vast nothings are forcing scientists to rewrite the rules of cosmic evolution. How did such enormous emptiness come to be? What can the absence of matter tell us about the invisible forces controlling everything? The answers challenge our deepest assumptions about how the cosmos builds itself, and it makes you wonder about our place in a universe defined more by emptiness than by light. The cosmic web isn't flat. It's a three-dimensional structure, incredibly complex. Galaxies aren't just scattered randomly. Gravity pulls them together into huge walls and winding filaments. It's a delicate, lacy architecture that stretches across everything we can see. And this design leaves behind enormous gaps. These spaces are so profoundly underpopulated, they go against our idea that matter should be spread out evenly. These are the cosmic voids. Calling them simply empty isn't right, but to stand in the center of one would be profound isolation. The nearest major galaxies would be tens of millions of light years away. Just faint smudges in an ocean of near nothingness. Inside these voids, the density of all matter, stars, gas, the dark matter that binds everything, it can be less than 1/10 of the universe's average. They're not perfect vacuums. A few lonely field galaxies drift through, often small and irregular, like ships lost at sea. And there's a whisper-thin haze of intergalactic gas. But compared to the bustling metropolises of galaxy clusters, these regions are cosmic deserts. Their very existence, these staggering pockets of near nothing, is the first major clue. That the universe's growth wasn't smooth. It wasn't a uniform process. It tells us the initial seeds of structure had imperfections, tiny ripples, that gravity magnified over billions of years. Into a landscape of extreme contrasts. Defining the void is just the beginning. The real mystery is how something this vast, this empty, could ever come to be. These voids, they weren't predicted. They were just stumbled on. The first real map of that cosmic desert, it wasn't made by a supercomputer. It was made by patient eyes, looking at photographic plates in the late 70s. Astronomers Stephen Gregory, Laird Thompson, William Tift. They were charting galaxy positions, and a strange pattern came up. They weren't just finding clusters. They were finding the spaces in between. And some of those spaces, they were alarmingly large, inexplicably large. It was like ancient cartographers mapping a coastline, and then realizing they were looking at the edge of a continent, with a vast ocean just stretching out beyond it. The big discovery came in 1981, in the constellation Boötes. What they found wasn't an object, it was the absence of objects. The Boötes void, a spherical region of space about 330 million light years across. In a volume that large, the standard models said there should be thousands of galaxies. But the surveys showed only a handful, just a pitiful few. It was a staggering emptiness, a bubble in the fabric of the universe so vast, you could put thousands of Milky Ways in there, end to end, with nothing but darkness in between. That was the moment everything changed. The assumption of a smooth, uniform universe, that cornerstone of cosmology, it just shattered. Emptiness wasn't a mistake. It wasn't an accident. It was a feature, a fundamental part of the cosmic architecture. The Boötes void proved that the universe's structure was defined as much by what was missing as by what was there. It opened a whole new frontier, where the questions weren't about stars and galaxies anymore. They were about the silent, sprawling deserts that separate them. And it forced one unsettling question onto the table. If gravity pulls matter together, what kind of force could carve out a hole this big? The emptiness is on a scale that's hard to even grasp. Light is the fastest thing there is, and for a photon to cross one of the largest voids, it would take hundreds of millions of years. On that entire journey, it would meet almost nothing. No stars, no galaxies, just the occasional stray atom. If you put our own galaxy, the Milky Way, into the center of a void like Boötes, everything would change. Our neighborhood would become a place of deep solitude. Andromeda, our closest large galaxy, wouldn't be a smudge in our sky anymore. It would be tens of millions of light-years away. An island in an ocean of darkness. The other galaxies inside the void would be faint, lonely dwarfs, little comfort against all that black. And we know these voids are real. We've learned to map the architecture of nothingness. Projects like the Sloan Digital Sky Survey did something revolutionary. They didn't just catalog stars. They used the redshift from millions of galaxies to build a 3D atlas of the cosmos. The result confirmed the cosmic web. But more than that, it revealed the negative space. The bubbles. The data shows the universe isn't a random scatter. It's a frothy sea of galaxy filaments surrounding immense spherical cavities. It's a map of emptiness. The KBC Void, for example, suggests we might even live in a slightly underdense region ourselves, a smaller bubble within the larger structure. That sheer size is the mystery. Gravity pulls things together. It's a force of attraction. So how does a region hundreds of millions of light-years across stay so empty? What process could clear out matter on that scale? And then keep it cleared for billions of years? The voids aren't passive holes. They're active, dynamic entities. Their immense scale is a direct challenge. A clue written in negative space about the forces that shaped the universe from the very beginning. A void starts with a whisper. You have to go back to the very beginning. The universe, just a fraction of a second old, wasn't perfectly smooth. It couldn't be. There were tiny ripples, random ones, in the density of everything. Some spots were a little denser. Some spots were a little emptier. These are the primordial fluctuations. They're the seeds for everything, for the clusters of galaxies and for the dark voids. Gravity works on these seeds. It's an amplifier. Over billions of years it pulls matter from the less dense places toward the denser ones. It's like water draining. The low spots don't just stay low, they get lower, as everything flows toward the hills. In the cosmos, the slightly underdense regions, those whispers, they expand faster. As the universe grows, they stretch. Matter gets siphoned away, drawn toward the pull of the denser filaments, the knots that become galaxy clusters. A minor dimple becomes a bowl, then a crater, then a chasm. Over time, that chasm becomes a void. Think of bread dough rising. The yeast isn't perfectly mixed. Where it's less concentrated, larger air bubbles form. The universe is that dough expanding. The voids are those colossal bubbles. Their emptiness stretches as the cosmic loaf rises. And this shows a symmetry. The cosmic web isn't just the bright threads. It's a unified structure. The dense filaments and the empty voids, they're two sides of the same coin. Born from the same imperfections, shaped by the same gravity, one can't exist without the other. The glittering cities of galaxies define the borders of the deserts. And the deserts define the cities. So a void isn't a mistake. It's the amplified echo of a quantum whisper from the dawn of time. It's the signature of the universe's first uneven breath. Written large across the sky, gravity carves out these voids, but now something else controls them. Dark energy. It's this repulsive pressure everywhere in space, making the universe expand faster. And inside the voids, dark energy doesn't just exist. It's in charge. Imagine a void as a nearly empty room. The galaxies and gas, they're like a few pieces of furniture pushed into a corner. Their gravity is very weak. There's almost nothing pulling back against dark energy's push. So in these huge, sparse regions, the repulsive force meets hardly any resistance. The result is dramatic. Voids don't just expand with everything else, they expand faster. They're like cosmic accelerators, stretching quicker than the dense clusters around them. That makes a void more than just a hole. It becomes a kind of laboratory, a natural experiment on a scale of billions of light years. If you measure how voids grow, their shapes, how fast they expand over time, you can take the temperature of dark energy. You can probe its strength, see if it's consistent, Is dark energy the same now as it was 7 billion years ago? The evolution of a void might tell you. Because its growth is a tug of war. On one side, the weak gravity of the sparse matter, trying to hold the void together, keep it from growing too fast. On the other side, the constant push of dark energy, trying to inflate it. By watching which side wins and by how much, you get an indirect measure of dark energy's power. It's a workaround. We can't see dark energy, we can't touch it. But we can see its fingerprint on the architecture of emptiness. The stretching of these colossal bubbles is our clearest signal. The invisible hand at work. So the story of voids is a double mystery. They're shaped by the absence of gravity's pull, but they're driven now by the presence of dark energy's push. They are not just fossils, they are active, expanding faster and faster into the future. But there's life in all that emptiness, not life like ours, but galactic life. Out in the cosmic desert, you have these islands of light. The loneliest ones, they're called void galaxies, and that isolation makes them something special. There's one galaxy, MCG plus 01020015. Astronomers call it the loneliest galaxy. It's in a part of space so empty. The next big galaxy is over 1 million light-years away. That's more than 50 times the distance from us to Andromeda. Picture a single city glowing, and the next city is so far you'd never see its light. That's what it's like in a void. These isolated systems aren't like the ones in crowded clusters. In those dense places, galaxies are always bumping into each other, merging, getting torn apart by gravity. It's violent, it shapes them, but a void galaxy is a hermit. It grows up in quiet. With no close neighbors, it might never have a major merger. Its evolution is slower. More peaceful, it directs itself, so you get a different kind of galaxy. Void galaxies are usually smaller. They're often bluer, which means they're still forming stars. And they are rich in gas. Their raw material hasn't been stripped away by a busy environment. So they can form stars steadily for billions of years. They're like time capsules. They preserve a gentler path of growth. That makes them a perfect control sample for scientists. To see how environment shapes a galaxy, you need to see one that's been left alone. By studying these hermits, we can separate nature from nurture. We can ask, what's the baseline state for a galaxy when it isn't bullied or merged? The void galaxies show us. Their quiet, gas-rich lives show how much the drama of crowded clusters changes the others. They're the pure signal in all the cosmic noise, and in their deep solitude, they hold the key to understanding everything else. Void galaxies evolve in quiet isolation, and that leads to a deeper puzzle. The matter they're made of, the gas for stars, it's missing. It's the missing baryon problem. Baryons are the building blocks of everything you see. Stars, planets, us, all baryonic matter. Our models of the Big Bang tell us exactly how much of this ordinary matter the universe should have. The math is clear, but when you add up all the visible matter galaxies, stars, glowing gas, the total comes up short. Very short. A significant part of the universe's ordinary matter is just unaccounted for. So where is it? The leading theory points to the voids, not the galaxies, but the emptiness between them. Scientists think a large fraction of these missing baryons could be hiding there. As an incredibly thin, hot gas, the warm, hot intergalactic medium, it's like a faint cosmic fog, a web of superheated filaments too tenuous to glow. Threading through the dark deserts, this gas isn't cold enough to form stars. It isn't dense enough to be easily seen. It's the ghost in the machine. And if it exists, the voids are its home. They could hold vast reservoirs of this elusive material, strung along the faintest threads of the cosmic web. Threads that even emptiness can't fully erase. The challenge is huge. Detecting something that barely exists across hundreds of millions of light years. It pushes technology to its limits. We look for subtle imprints. How this diffuse gas might absorb or distort light from distant quasars, acting as a cosmic filter. Or we search for faint X-ray signatures, A whisper of heat from gas that's millions of degrees, yet incredibly sparse. Every time we don't detect it, that's a clue. It tells us the gas is even more elusive, more spread out than we thought. This search is crucial, because if we can't find this matter, our entire inventory of the cosmos is wrong. It's not just that we misunderstand the voids. We misunderstand the basic ledger of what the universe is made from. How that material flows from these empty regions to eventually build the galaxies we see. The silence of the voids. It might be hiding the answer to one of cosmology's most fundamental questions. The silence of the voids. It's not just about missing matter. Some of these empty spaces are just too big. They're too big for the timeline we have, the Boötes void. It's 330 million light-years across. To get that big, it would have had to start from a tiny seed of emptiness, right at the beginning. But the math from our standard model, it struggles with that. The universe is 13.8 billion years old. That's a long time. But for gravity to carve out something that vast, starting from the tiny ripples we think were there, it might not be enough time. It's like blowing up a balloon and finding a bubble inside that's bigger than the balloon. The physics doesn't add up. That's the too big to form problem. These largest voids, they're overachievers. They grew faster than they should have, or they started bigger. So that means something. It forces a re-examination. Either our understanding of the starting conditions is wrong, or something else helped them grow. One idea is about those first underdensities, the quantum whispers. Maybe they weren't all the same size. Maybe a few were born exceptionally large. A deeper dimple in the early fabric. That would give them a head start. To become the titans we see. Another idea looks at how voids evolve. Maybe they didn't grow alone. Galaxy clusters merge into superclusters. Voids could merge too. Two expanding bubbles of emptiness could meet. Their borders dissolve, and you get one colossal void. If that happens more than our simulations predict, it could explain the giants. But then there's a more intriguing possibility. Something beyond our standard model. An exotic phenomenon. A modification to gravity itself on the largest scales. Or an interaction with dark energy we don't understand. Something that gives voids an extra push. Their near-empty interiors are perfect for that. For subtle new forces to show themselves. Forces that would be drowned out in the crowded places in the galaxy clusters. This discrepancy, it's a direct challenge. The absence of structure on this scale is a message. It says the story we've written for the cosmos might be missing a chapter. A chapter written not in light, but in the darkness between the stars. The loneliest galaxies and the missing matter, they are part of it. But there's a third thing. A quieter challenge. It comes from the geometry of the emptiness itself. The lambda cold dark matter model, our main theory of the universe, it's a masterpiece. It makes very specific predictions, not just about where galaxies are, but about the voids between them, the shapes, the sizes. It says voids should have a certain statistical profile. Mostly spherical but a little squashed, like a deflated ball, and their sizes should follow a pattern. Many small ones, fewer gigantic ones. For decades, that framework matched what we saw. But now, with better maps of the cosmic web, there are tiny cracks. The voids are whispering the story might be slightly off. Observations show subtle tensions. Some voids look more perfectly round than the simulations say. Others seem more stretched. Elongated like cosmic sausages. Even the number of the largest voids might not match perfectly. These aren't glaring contradictions, they're faint discrepancies, the kind you see when you look with a sharper lens. It's like a master painter's signature. From across the room it looked perfect, but with a magnifying glass you see one brushstroke that doesn't match the artist's known technique. It doesn't mean the painting is fake. But it asks a question. Why is that stroke there? These mismatches are stress tests for our whole understanding of cosmic structure. They could point to refinements we need inside the model itself. Maybe our assumptions about dark matter are too simple. Maybe it interacts with itself in subtle ways we haven't accounted for. influencing how voids expand and merge. Or the physics of ordinary matter, the baryons, might play a bigger role. The way gas heats up, gets pushed around by exploding stars. That could reshape the boundaries of these empty regions. Even neutrinos, those ghostly particles, they have a tiny amount of mass. Enough, maybe, to influence the growth of the largest structures over billions of years. Each of these factors is a dial we can adjust in our simulations. The shapes of the voids are telling us which dials to turn. They're a cosmic calibration tool written in negative space. So these quiet tensions aren't a sign of failure. They're a sign of progress. They show our models have become so precise we can now see where they might be incomplete. The voids, in their profound emptiness, are providing the cleanest possible laboratory. A place where the faintest signals from new physics aren't drowned out by the chaos of galaxies. Every irregular shape, every unexpected number is a clue, a message from the dark, asking us to look closer, to think deeper. The silence, it seems, has a lot to say. This quiet evolution is a real paradox. Out in the cosmic desert, you find what looks like a contradiction. These void galaxies, these lonely islands, they're often surrounded by vast potential. The models say there should be immense reservoirs of primordial gas drifting through these empty regions. All that raw fuel for making stars. And with no galactic neighbors around to steal it, you'd expect a frenzy of creation. A constant firework display out in the deep dark. But the telescopes show a different story, a much quieter one. A lot of these isolated galaxies are surprisingly anemic. Their star formation rates are low. They're not the bustling factories you'd expect from all that gas. They're underperforming. It's like finding a lone tree in the middle of a vast, fertile plain, and the tree is stunted. Barely growing. The resources are there, but something's preventing their use. That inefficiency gets to the heart of how we think galaxies grow. The standard models often assume a straightforward relationship. More available gas equals more stars. But the void galaxies break that rule. They show us that the environment of profound emptiness imposes a new physics, a set of rules we're just starting to understand. The gas in these regions, while plentiful in total volume, might be too spread out, too diffuse. Imagine trying to light a campfire not with kindling but with a cloud of sawdust. The particles are too far apart to catch and sustain a flame. In a void, the hydrogen gas might be so thinly distributed it can't collapse under its own gravity. Can't form the dense clouds you need to birth stars. It just lingers, a faint, useless fog. There's another possibility, tied to the galaxy's own histories. Even a quiet, isolated galaxy has episodes of star formation. And when those first stars lived and died, especially the massive ones that go supernova, they unleashed tremendous energy. In a dense environment, that energy gets absorbed or disrupted by nearby gas clouds. But in a void with nothing to bump into, that feedback could have blasted the remaining gas far out into the intergalactic medium. Could have heated it so much it can't cool down and fall back in to form new stars. The galaxy, in a sense, sterilized its own future. It used up its first batch of fuel and then made the rest unusable. This self-regulating mechanism might be the dominant story in the voids. It creates galaxies that aren't just isolated but stuck, frozen in a state of quiet underachievement. Their deep solitude isn't a guarantee of peaceful growth. It can be a recipe for stagnation. This paradox forces astrophysicists to refine their simulations to account for the unique conditions of ultra-low density. It shows galaxy formation isn't a one-size-fits-all process. The vibrant cities in the cosmic web follow one set of rules, shaped by crowding and collision. The hermits in the desert follow another, shaped by silence and feedback. And by studying these quiet underperformers, we learn that having all the raw materials in the world means nothing if you can't bring them together. We need a laboratory, but you can't experiment on a void. You can't speed up billions of years, so scientists do the next best thing. They build a universe inside a supercomputer. These are cosmological simulations, Projects like Illustris TNG or UCHU, they're not animations. They're virtual universes born from equations. You start with the initial conditions of the Big Bang. You set in motion billions of particles, even trillions. Each one is a parcel of dark matter or gas. The laws of physics are programmed in. Gravity pulls. Gas cools and collapses. Stars ignite and explode. Over eons of simulated time, a cosmic web emerges, and within it, the voids. Creating these digital cosmos is one of the most demanding tasks in science. The challenge is scale and focus. To study a void properly, you need to simulate an enormous volume of space, a region big enough to contain several of these colossal bubbles. Otherwise, you're just looking at the edge of something. But within that huge volume, you also need incredible resolution. You need to see the faint, wispy filaments that thread the emptiness. You need to track the lonely galaxies drifting inside. And you need to model the complex physics of the gas between them. How it heats, how it cools, how it responds to blast waves from distant supernova. It's a staggering balancing act, simulating vast emptiness with exquisite detail. It's like trying to forecast the global climate, but you also need to accurately model the formation of every single raindrop in a quiet forest. The computational power required is almost beyond comprehension. The largest simulations run on the world's most powerful supercomputers for months. They generate petabytes of data. A snapshot of everything, everywhere, at a moment in cosmic time. These simulations are our proving grounds when we have a new idea. Maybe about how dark energy pushes on voids, or how supernova feedback stifles star formation in isolation. We can code it into the simulation and press play. We can watch over billions of simulated years if our idea creates a universe that looks like the one we actually see. This is where the quiet tension becomes a clear signal. When the most advanced simulations running our best theories consistently produce voids that are the wrong shape, or the wrong size, or that contain galaxies that are too active compared to the real, quiet ones we observe, that is not a failure. It's a discovery. The simulation is telling us politely but firmly that our physics is incomplete, that a piece of the puzzle is missing. It forces a cycle of refinement. Scientists go back to the code. They tweak the strength of feedback. They test new models for dark matter behavior. They add in the subtle effects of magnetic fields or cosmic rays. Then they run the universe again. Each iteration, each mismatch between the digital void and the real one, guides us closer. The emptiness, through the mirror of the simulation, is teaching us how to fill in the blanks. The universe's emptiness has its own ecosystem. Not every void is a giant like Boötes. They exist in a hierarchy. At the smallest scale, you have mini voids. These are the tiny bubbles inside the filaments themselves. The cosmic web isn't a solid rope. It's a bundle of threads with small gaps woven between them. Those are the capillaries of emptiness. Then you have the classic voids, the ones we usually picture. Medium-sized spherical regions, each bounded by the great walls and sheets of galaxies. They're like rooms in a mansion, defined by the walls around them, and at the top are the supervoids, the continents of nothingness, regions so vast they can contain smaller voids inside them. Like a massive lake holding smaller pools, they're the dominant features, the true monarchs of empty space. This ecology isn't static, it's a dynamic system. Smaller voids merge. The walls between them thin and dissolve as both regions expand, until they coalesce into a single, larger void. It's like watching soap bubbles touch and become one. Over billions of years, the void population shifts. The number of small voids decreases as they are swallowed by their growing neighbors. The average size of emptiness in the universe increases. This merging is a critical part of the cosmic web's life cycle. It shows the architecture of nothingness evolves alongside the architecture of light. Where a void sits in this hierarchy, its cosmic address dictates everything inside it. A small void nestled in a dense filament has a very different environment from a supervoid floating in the deepest hinterlands. The pressure from the surrounding structures is immense. A void near a massive supercluster is squeezed. Its shape gets distorted by the gravitational pull of all that nearby mass. Its expansion might be slightly restrained. The few galaxies inside it might feel the tidal tug of that external density. It influences how they rotate, how they accrete gas. In contrast, a void in a truly isolated region expands more freely. A perfect sphere of near-nothingness growing into the darkness. Its resident galaxies are the ultimate hermits. Evolving with almost no outside influence, mapping this hierarchy is now a central goal. By cataloging voids by size, shape, and environment, cosmologists are creating a field guide to emptiness. This classification is more than just labeling. It's crucial for understanding cosmic evolution. Because matter is always in motion, the flow isn't just toward the dense clusters. It's also an outflow from the emptying voids. As a void expands and merges, it pushes matter toward its edges, feeding the filaments and walls that surround it. The hierarchy of voids, therefore, charts the pathways. It shows how the raw material of the universe is funneled from the barren deserts into the fertile rivers of the cosmic web, and ultimately into the glittering cities of galaxies. To understand how the universe builds itself, you have to understand the life cycle of its emptiness. The true nature of a void is written in the dark. Not the darkness of space, but the darkness of the unseen. That's where the mystery of dark matter meets the architecture of emptiness. Voids, these places with almost no stars or galaxies, they become our clearest window. A window into the invisible scaffolding that holds everything together. If you want to map dark matter, you don't look where it's crowded, where it's tangled with all the luminous stuff. You look where it's almost alone, you look into the void. The logic is simple. A void has very little ordinary matter, the stuff we can see. So any significant gravity we detect there, inside that empty region, it has to come from something else. And that something is dark matter. By studying the subtle gravitational effects in a void, you can take an X-ray of its dark matter skeleton. The main tool for this is weak gravitational lensing. Imagine light from a galaxy far behind a void. As that light travels through the void to reach us, the gravity of all the matter inside, which is mostly dark matter, it bends the light's path. Just slightly, it doesn't make rings or arcs. The distortion is incredibly faint, a tiny shearing of the galaxy's shape. But if you measure this warping for thousands of galaxies, for thousands of background galaxies, you can rebuild a map. You can trace the void's gravitational footprint. You can weigh the nothingness, and what these maps show is a structure, a profound one. Voids aren't perfect vacuums of dark matter. They aren't holes punched through the invisible web. They're smooth, shallow basins. Think of a vast valley, gently sloping. The dark matter is still there, but its density is much lower. Far lower than in the crowded filaments. It forms a diffuse halo, a ghostly halo that permeates the entire empty region. This finding is crucial. It tells us that dark matter, whatever it is, was also subject to those primordial ripples. It was also pushed out of the underdense regions, but not completely. A faint residue remains, and that residue defines the void's shape. It governs how the void expands. This smooth distribution is a test, a direct test for our theories. Our leading model says dark matter is cold. That means its particles moved slowly early on, letting it clump easily into the seeds of structure. Cold dark matter predicts a certain profile for these void halos. A specific way the density should change from the empty center out to the walls. But what if dark matter is more complex? Some other theories suggest the particles might interact. They might interact with each other through some unknown force. This self-interacting dark matter would behave differently. In a crowded cluster, particles bouncing off each other could smooth out the dense cores. But in a void, that same interaction might stop the dark matter from draining away completely. It could leave a slightly different distribution, a flatter one in the center. So by measuring the dark matter topography of thousands of voids meticulously, Astronomers are running an experiment. A grand one. They are asking the emptiness to tell them what the dark stuff is made of. The quiet, diffuse halo in a void is a fingerprint, a cosmic fingerprint. And by learning to read its faint lines, we might finally identify it, the invisible substance that shapes everything. The oldest light in the universe remembers the voids. That light is the cosmic microwave background, a glow from when the cosmos was just 380,000 years old, a picture of the infant universe. And as that ancient radiation travels for billions of years to reach us, it's not moving through empty, static space. It's passing through the evolving cosmic web, the growing voids and the dense clusters, and that journey leaves a mark, a small change that's called the integrated Sachs-Wolf effect. It's subtle, but the implications are profound. You have a photon, a particle of that primordial light, starting its long trip. As it flies through space, it moves through regions of different gravity. The gravity of a massive cluster pulls on the photon. When the photon falls into that deep gravitational well, it gains energy, but then it climbs back out, and it loses that energy again. In a universe expanding at a steady rate, those gains and losses would cancel out perfectly. The photon would arrive with the same energy it started with. But our universe isn't expanding steadily. It's accelerating, driven by dark energy, and that changes the balance. Over cosmic time, the gravitational wells of clusters become shallower. The hills are being flattened as the universe stretches. So when our photon climbs out of a cluster's well, it doesn't have to work as hard. It doesn't lose all the energy it gained. It arrives with a tiny bit more. That photon appears slightly hotter or bluer than the average background. Then consider the opposite trip, a photon passing through a vast, growing void. A void is a gravitational hill, a region of lower density. Climbing this hill costs the photon energy. It becomes slightly redder, cooler, but as the void expands faster because of dark energy, that hill becomes steeper. So when the photon descends the other side, it gains back more energy than it lost. The net result: a photon passing through a large, expanding void also arrives with a tiny bit more energy. A hot imprint. Detecting this signal is a monumental challenge. We're looking for temperature variations in the cosmic microwave background of just a few millionths of a degree. Variations that line up with the positions of the largest voids and clusters in the nearby universe. It's like trying to hear a single instrument tuning in a symphony hall from a mile away. But after years of analysis, combining galaxy surveys with detailed maps of the cosmic microwave background, astronomers have heard it. They've detected the integrated Sachs-Wolf effect. This is more than a technical triumph. It's direct, observational evidence that the gravitational landscape of the universe is changing in a way that only dark energy can explain. The voids are not silent. They are singing. And their song, imprinted on the first light of creation, confirms the presence of the mysterious force that is stretching the cosmos apart. It's a breathtaking connection. The study of the largest empty spaces, the cosmic nothings, gives us one of our clearest confirmations of the accelerated expansion of everything. We need new ears to hear the void's full symphony. The next telescopes will turn whispers into a chorus. They're being built now with one goal: to map the darkness with a clarity we've never had. On a mountaintop in Chile, the Vera C. Rubin Observatory is preparing for a staggering mission. Its legacy survey of space and time will scan the whole southern sky, night after night, for 10 years. It won't just find galaxies. It will catalog billions of them, pinpointing their positions and distances with such immense numbers that the three-dimensional map of the cosmic web will leap into focus. The voids won't just be seen. They'll be measured, cataloged, studied in populations of thousands. We'll see the full hierarchy, from the tiniest bubbles to the continental supervoids, with a statistical power that turns hints into laws. It's the ultimate census of emptiness. Meanwhile, in the silent cold of space, another eye is opening. The Euclid Space Telescope, free from Earth's atmospheric blur, has a different specialty. It will measure galaxy shapes with exquisite, almost impossible precision. That's the key to weak gravitational lensing. By analyzing the subtle warping of millions of galaxy shapes behind thousands of voids, Euclid will build the most detailed maps yet of the dark matter halos inside these empty regions. It will weigh the ghostly valleys, and in that weight we might find the signature of dark matter's true nature. Is it cold and non-interacting, or does it show the faintest hint of something else? The void's smooth dark matter distribution will tell the tale. Then there's the hunt for the missing stuff itself. The warm, hot intergalactic medium, that elusive fog of baryons. To find it, we have to look not with optical light, but with X-rays. That's the goal of future observatories like Athena. Designed to detect the faintest X-ray glow from million-degree gas, Athena will point its instruments at the deepest voids. If the whim is there, strung along the faintest filaments like a cosmic spiderweb, Athena should see its whisper-thin emission. It could finally solve the missing baryon problem, showing us where half the ordinary matter in the universe has been hiding for billions of years. Together, these instruments are a new era. They'll transform voids from mysterious, shadowy gaps into the most precise cosmological tools we have. They're laboratories built by the universe itself, on a scale we could never replicate. Within their expansive silence, we'll test the laws of physics with a rigor that crowded space could never allow. We'll either confirm our current models of dark matter and dark energy with unshakable certainty, or the voids will reveal something entirely new. A subtle crack in the foundation, pointing toward a deeper, stranger truth. The story of the cosmos is written in the empty spaces between the stars, and we are just now learning how to read it. The cosmos might find its final shape in the emptiness. Voids grow faster than everything else, pushed by dark energy. And that's not just a quirk of now. It's a preview, a look at a future so far away it's hard to even picture. If dark energy stays constant or gets stronger, then the acceleration we see today is just the start. The voids won't just expand, they'll consume. You can think of the cosmic web like a tapestry. The threads are the galaxy filaments, gravity holding them together. The dark patches are the voids. Now picture that tapestry being stretched faster and faster. The threads, under that tension, they start to thin. They get more tenuous. The dense knots where galaxies cluster, they hold on the longest, but even their gravity has a limit. Eventually, the accelerating expansion overcomes it. A galaxy cluster gets ripped apart. Its galaxies are flung into the growing void, becoming isolated islands. The filaments themselves get stretched until they snap. That grand architecture, built over billions of years, gets taken apart. The universe becomes a sea of darkness, dotted with solitary, fading galactic embers, each one receding from all the others at speeds that make communication impossible, even observation. This is a vision of the heat death, not as a uniform cold, but as a landscape of profound, irreversible isolation. And the voids are the engine of that isolation. They're the active force, dissolving the web they helped create. This speculative future, it gives a haunting significance to the voids we study now. They aren't passive fossils. They're living entities, and their growth rate is a direct measure of the power shaping the universe's final act. By tracking how a void's borders move, how its internal dynamics change over cosmic time, we're reading the first pages of the last chapter. The data we gather now on void mergers, on their shapes and expansion speeds, that's more than just cosmology. It's a form of cosmic prophecy. It tells us whether the tapestry will fray slowly, over hundreds of billions of years, or if a more dramatic unraveling is waiting. This connects the largest scales to the ultimate fate of all things. It's deeply poetic. The same emptiness that taught us about the universe's birth from quantum whispers now holds clues to its end. In their silent, relentless expansion, voids are the agents of a cosmic transformation. They remind us the universe isn't a static museum. It's a story still being written, a dynamic system where even nothingness has a leading role. And in that role, the voids offer a profound perspective. Sobering, the glittering cities of the cosmic web. For all their brilliance, they might be temporary. The true, enduring character of the universe could be one of vast, quiet, and ever-growing space. That profound emptiness gives you a quiet sense of our place. For centuries, we've seen the stars as the main feature. Their light and energy, the potential for life. We're made from starlight, living on a rock around one of them. So it's natural to think the galaxies are the point. But the cosmic voids tell a different story. They aren't the backdrop, they're the dominant reality. By volume, most of the universe isn't filled with stars or busy galaxies. It's filled with these huge, quiet, nearly empty regions. The glittering cities of the cosmic web are the rare exceptions. The vibrant neighborhoods in a cosmos that's mostly vast, dark, silent space. That challenges an anthropocentric view. Our whole existence needs density. We need matter, energy, complex chemistry. So we naturally go toward the parts of the universe like us. The dense, active, luminous parts. But that focus might give a distorted picture. The voids suggest the true character of the cosmos is spaciousness, stillness. The grand drama of galaxy collisions and star births is a local phenomenon. It plays out in crowded intersections of an otherwise serene, expansive landscape. In this view, we're not the center of anything. We live in a rare and special district, but our district is surrounded by a country of profound emptiness. It stretches farther than we can truly comprehend. That shifts how we might search for meaning. If we only study the bright spots, we're only reading a few pages of a very long book. To understand the whole story, we have to read the spaces between the words. The voids are those spaces. They're not meaningless blanks. They're integral to the narrative. They define the structure. They drive the evolution. They hold clues to the universe's origin, its ultimate fate. A complete picture of reality has to account for both presence and absence. The light and the dark, the dense and the diffuse. By trying to understand the voids, we're not turning away from the wonder of galaxies. We're adding a crucial, deeper context to that wonder. We're acknowledging the universe in its totality is a balance of extremes. Our home exists within a delicate and uncommon equilibrium. That perspective doesn't diminish our significance. But it does reframe it within a much grander and quieter scheme. Our cosmic address is inside a bubble of emptiness, not one of the giant voids, but a significant one, the Keenan, Barger, and Cowie void. The KBC Void, that places our local group, the Milky Way and Andromeda, inside a region about 2 billion light-years across, and it's emptier than the cosmic average. The matter density here is maybe 20 to 50% lower than the rest of the universe. We're not in a special, dense hub. We're out in the galactic suburbs. A quiet, underpopulated neighborhood, and that fact isn't just trivia. It has direct consequences for how we understand the universe's expansion. The rate of that expansion is the Hubble constant. Measuring it accurately is a major goal in cosmology. There are two primary ways to do it. One method looks locally at nearby galaxies and supernova to gauge how fast they're receding. The other method looks at the ancient universe using the cosmic microwave background to infer what the expansion rate should be today. These two methods are incredibly precise. But they give different answers. They stubbornly refuse to agree. That discrepancy is the Hubble tension. It's one of the biggest puzzles in science. Our location inside the KBC Void might be a key piece. Think of it like measuring the average slope of a vast, rolling hill, but you're standing in a small valley. If you only measure the ground right around your feet, your local measurement will suggest the hill is less steep than it truly is overall. In cosmic terms, living inside an underdense region means the gravitational pull of surrounding matter is weaker here. The space around us expands a little faster than it would in an average, denser region. So when we use nearby supernova to measure the Hubble constant, we might be getting a slightly inflated value. A local reading that's biased by our quiet address. This doesn't fully solve the Hubble tension, but it is a crucial correction. It reminds us our viewpoint isn't neutral. We're observing from a specific location with specific properties. To get the true, global picture, we have to account for the emptiness of our own backyard. The KBC Void transforms from a simple fact into an active participant in a major debate. It shows how the architecture of nothingness shapes not just galaxies, but the very numbers we use to describe the fate of everything. Our home in this gentle cosmic valley directly influences how we measure the universe's most fundamental behavior. Our cosmic neighborhood is quiet, but it's just one piece of a much larger puzzle. And when you take the standard model and bring it into these vast empty spaces, you get a tension. A real interesting tension. The peculiar properties of some voids have pushed scientists to look beyond the standard model. Beyond lambda cold dark matter, the emptiness becomes a proving ground for radical ideas. One major alternative is modified Newtonian dynamics, MND. It says our understanding of gravity is incomplete. On galactic scales, instead of dark matter, it says gravity behaves differently when the pull gets extremely weak. Like at the edges of galaxies, and that neatly explains galaxy rotation curves, without any dark matter, but MND has struggles, especially with galaxy clusters. Where it still seems to need some unseen mass, its relativistic extensions like tensor vector, scalar gravity, try to build a full theory, and this is where voids become critical. In the deep heart of a cosmic void, the gravitational field is the weakest it can be. In the whole universe, if gravity does have a different behavior in such an extreme low acceleration place, the effects should be most apparent there. Some studies suggest that the distribution of the few galaxies inside voids, their motions, or the way voids themselves expand, they might show subtle signatures. Signatures that fit a modified gravity picture better than the standard model with dark matter. It's a high-stakes test. Voids are a clean laboratory, free from the messy complications of crowded galactic centers. If the standard model's predictions fail in the emptiness, it could mean a fundamental rewrite of gravity itself. Beyond modified gravity, other exotic ideas get scrutinized too, against the void's silent testimony. Could dark energy interact with dark matter in some unknown way, changing how structures form? Could primordial magnetic fields, woven into space from the earliest moments, have influenced where matter collected and where it was repelled, shaping the void hierarchy we see today? Each of these theories makes specific predictions about the statistics of voids. Their sizes, their shapes, how many of each kind should exist. By mapping thousands of voids with new telescopes, cosmologists are running these theories through a cosmic filter. The voids serve as a magnifying glass for physics at its limits. In the crowded, violent environments of galaxy clusters, any signal of a new force is drowned out by the chaos of standard gravity and collisions. But in the serene, minimalist landscape of a void, even the faintest whisper of an alternative would stand out. A discrepancy there would echo loudly. So the standard model remains our best map of the cosmos. But the voids are the blank spaces on that map, where the inscription might read, "Here be dragons." They are the frontier, where our current understanding is stretched thinnest, and where the next revolution in physics may first announce itself. The fear of emptiness is ancient. It's in our language, in our art. Long before telescopes, people looked at blank spaces on maps or at the dark gaps between stars, and they felt a deep unease. Nature abhors a vacuum, that was the idea. Horror vacui, the fear of the void. It was a philosophical principle, an artistic one. An empty space was seen as unnatural. It needed to be filled, decorated, completed. You see it in medieval manuscripts, every inch of parchment covered in intricate designs. You see it in old maps, where unknown oceans were filled with sea monsters, and the edges of the world had warnings. Emptiness wasn't neutral. It was a realm of potential danger, the unknown, things not yet defined. The cosmic voids of modern astronomy tap right into that archetype. They are the ultimate unknown on the grandest scale. Not a blank spot on parchment, but a blank spot in the universe itself. And like our ancestors, we can't help but project stories onto that darkness. Science fiction has used the void as a narrative device for a long time. It's the setting for ultimate isolation, a lone ship drifting for centuries, crew in suspended animation. It's a place of mystery where physics breaks down, and alien artifacts of incomprehensible age lie dormant. Sometimes it's a realm of transcendence, where characters encounter beings of pure energy, or confront the fundamental nature of reality. From the eerie silence in 2001, a space odyssey to the vast territories in Star Trek, the void is more than a backdrop. It's a character. It represents the final frontier, but also the psychological frontier, confronting absolute solitude and scale. These stories give emotional texture to the cold data of cosmology. They let us feel, in a human way, what it might mean to be truly alone in a bubble of nothingness, hundreds of millions of light-years wide. That cultural resonance enriches the scientific pursuit. When an astronomer studies a void, they're not just analyzing redshift data and density maps. They're probing a space that has occupied the human imagination for millennia. The void is a blank canvas, but it's never truly blank for us. We fill it with our questions, our fears, our hopes. We see in it a reflection of our own smallness, and also of our boundless curiosity. So the journey to understand these real voids becomes a bridge. It connects the empirical, evidence-based world of modern cosmology with the ancient, narrative-driven human need to find meaning in the cosmos. The voids challenge us scientifically, but they speak to something older too. They remind us that our exploration of the universe isn't just a cataloging of objects. It's a continuing conversation between what is out there and what we, as storytellers and meaning makers, bring to it. The silence of the void invites us to listen. And in doing so, to hear the echoes of our own wonder. That profound silence can also be a powerful classroom. If you're teaching the structure of the universe, cosmic voids are a surprisingly clear entry point. They turn this abstract, three-dimensional web into something almost tangible. It's far easier for a student to picture the contrast, a bustling city of galaxies versus a sprawling, empty desert, than to start with the complex physics of a dense cluster. That stark difference makes the entire cosmic architecture click. You can use simple, everyday objects to model these ideas. A cluster of soap bubbles merging, where the empty spaces between them grow and connect. Or a block of Swiss cheese, where the holes represent the voids in a solid matrix of matter. Even the classic raisin bread dough rising shows how the spaces between the raisins, the voids, expand faster than the dough itself. These analogies aren't just cute. They're direct pathways. The expanding dough illustrates how underdense regions grow more quickly, and the way light might subtly change as it passes through these growing voids touches on the integrated Sachs-Wolf effect, which links the ancient cosmic microwave background to the dark energy of today. By starting with the holes in the cosmic cheese, a teacher can spark a chain of curiosity. Why is it so empty? What force is making it grow? What does that tell us about the invisible stuff holding galaxies together? That line of questioning leads students into the deepest mysteries of dark energy and dark matter, and how environment shapes a galaxy's life. It inverts the traditional approach. Instead of building up from stars to galaxies to clusters, which can feel overwhelming, you start with the negative space. You define the universe by what's missing. And in doing so, you make the luminous structure that remains. The glittering filaments and walls stand out in brilliant relief. The voids become a narrative device, a story of absence that explains presence. They make the scale of the cosmos not just a number, but a felt experience. A student can grasp the idea of 100 million light-year desert in a way they might never grasp the math of a galaxy cluster's merger. So the greatest emptiness becomes one of our most effective tools for illuminating the whole. The search for emptiness is teaching us to find patterns in everything. That's the unexpected legacy of void cosmology. To map these huge bubbles of nothing, scientists had to invent new ways of seeing. You can't just point a telescope at a void and take a picture of the dark. You have to infer its shape from the galaxies that outline it. That means sifting through the positions of millions of galaxies from surveys like Sloan, looking for the statistically significant absence of everything. It's a problem of pattern recognition, but on a cosmic scale. The algorithms they built to solve it had to be brilliant. They had to define the fuzzy, three-dimensional boundaries of emptiness in a sparse and noisy sea of data points. They had to distinguish a true, evolving void from just a random, temporary gap in the distribution. This challenge pushed data science into new territory. It led to the adoption of powerful mathematical tools like topological data analysis. This framework doesn't just look at where points are. It studies the shape of the data itself. It asks, what are the holes in this data set? What are its cavities and tunnels? For the cosmic web, the answer is literal. The voids are the topological holes. A technique called persistent homology lets researchers quantify these voids, to measure their size, their stability across different scales, and their significance against random chance. It gives us a rigorous, mathematical language for describing nothingness, and that language is turning out to be universal. The same algorithms that find billion light-year voids in galaxy surveys are now being used to find holes in very different kinds of networks. In neuroscience, they help map the voids in the connectome, the empty spaces in the web of neural connections, which might be just as crucial to brain function as the connections themselves. In materials science, they analyze the microscopic pores and cavities in a sponge like metal or a new battery compound, where the emptiness defines the material's strength, its conductivity, its very purpose. In epidemiology, they can identify unexpected gaps in the spread of a virus, pointing to hidden factors of immunity or behavior. The cosmic quest to understand the architecture of absence has given us, in turn, a new lens for presence. It's created a toolkit for finding meaning in sparse, complex data across countless fields. So when cosmologists run their void-finding codes on a supercomputer, they're doing more than astronomy. They're stress-testing a set of powerful ideas. Ideas about shape, structure, and significance that began with the mystery of the Boötes void and now help us decipher the human brain, design better materials, and understand complex systems here on Earth. The study of the largest empty spaces is, ironically, filling in critical gaps in our knowledge across the entire landscape of science. Mapping the architecture of emptiness is a huge job. It needs more eyes than any one team could ever have, so the work leaves the professionals. It becomes something everyone can join. Finding cosmic voids is now a shared human project through citizen science. There are online platforms like Zooniverse. They host projects where anyone can help astronomers. You get shown images from big sky surveys, the Sloan Digital Sky Survey, the Vera C. Rubin Observatory soon to launch, and the task is simple but crucial. You classify galaxies. Is that fuzzy blob a spiral or an elliptical? Is it merging with another one? Thousands of people making these classifications. They're building the most detailed catalog of the cosmic web we've ever had. And from that catalog, we draw the boundaries of the voids. Every click, every classification, is a stitch in the map of the universe, a direct contribution to the science that defines these empty regions. This process does something. It turns an abstract idea into a tactile experience. You spend an evening classifying distant galaxies. You start to internalize the scale. You see the sheer number of islands in the sky, and you start to notice the gaps between them. You're not just learning about voids, you're helping to find them. This democratizes discovery. It builds a bridge. It connects personal curiosity to the frontier of human knowledge. A person at their kitchen table becomes part of the same project that runs on the world's most powerful supercomputers. They gain an appreciation for the work behind every headline about dark energy or the cosmic web. It fosters a deeper understanding, a more personal one, of our place in this grand structure. We are not just passive observers of a universe with brilliant cities and dark deserts. Through these collective efforts, we become active participants in mapping it. The voids stop being distant, intimidating mysteries. They become puzzles we are all working to solve together. It transforms the awe of the cosmos into a shared sense of wonder and belonging. We still have these deep, persistent questions, that elusive gas, the warm, hot intergalactic medium. We think it's there, threading the voids. But its exact temperature, how it's distributed, is it in faint, wispy filaments, or is it more of a uniform, diffuse fog? Pinning that down is critical. It would finally solve the missing Baryon problem. It would tell us how ordinary matter cycles back from the deserts into the galaxies. Then there are the giants. Like the Boötes void, their sheer size keeps whispering that our timeline might be off. Do these colossal bubbles need a new ingredient in our cosmic recipe? A modification to gravity, maybe? Or a strange behavior in dark matter that gave them an extra push? Or did they just form from exceptionally large seeds in the early universe? We still don't know for sure. You look deeper into the emptiness and more mysteries appear. Magnetic fields. We know they exist within galaxies and clusters, woven by stellar winds and supernova. But do magnetic fields also permeate the voids themselves? If they do, they'd be unimaginably faint. Maybe seeded in the universe's infancy, but even a whisper of a magnetic field could influence how that tenuous gas moves. How it might eventually cool and collapse to feed a lonely void galaxy. It's a subtle force that could shape evolution in the quietest places. And that leads to the most speculative frontier. Could voids be home to something truly exotic? Forms of matter or energy that are so subtle, so weakly interacting, they only reveal themselves in regions of ultra-low density. In the crowded environment of a galaxy cluster, any signal from a phantom like that would be drowned out. But in the pristine silence of a void, its faint signature might finally be detectable. These aren't fringe ideas. They're serious considerations at the edge of cosmology. Each unanswered question acts like a beacon, drawing researchers toward new telescopes, more powerful simulations, more creative theories. It ensures the study of cosmic voids will never become a closed book. It's a living field where every answer seems to uncover two new questions. These vast pockets of nothingness, once seen as mere blanks on the map, are now the very places where our understanding of everything is most rigorously tested. The silence of the voids is a language we're trying to translate. They're not just blank spots. They've become a kind of Rosetta Stone for the universe. A single key that can unlock multiple mysteries. By studying what's not there, we learn about the forces that shape everything that is. That emptiness is a rich source of information. It tells us about dark energy. We can't see it, but we can watch its handiwork. These cosmic bubbles expand faster than average. Their growth rate measures dark energy's strength. An experiment on a scale of hundreds of millions of light years. And then there's the subtle warping of light. Galaxies behind a void, their light faintly lensed. That lets us weigh the void's ghostly halo of dark matter. Inside, where ordinary matter is scant, any significant gravity has to come from the invisible stuff. The void becomes a clean laboratory, a minimalist place to probe its distribution. These empty regions also test galaxy formation, in the most extreme environment. The lonely void galaxies evolve in profound isolation. They show us a baseline state, how a galaxy grows when it isn't bullied or merged with neighbors. Their quiet, underachieving lives force us to refine our models, to account for the physics of near-total solitude, and on the largest scales, the very existence of the largest voids. Their shapes and numbers, it's a stress test for our entire standard model of cosmology. Do their statistics match lambda cold dark matter, or do the discrepancies point toward something new? Modified gravity, a more complex dark sector. This makes the investigation of voids a holistic approach. It bridges the largest questions and the smallest details. Instead of studying dark energy, dark matter, and galaxy evolution as separate puzzles, you can look at a single void, see all these mysteries interacting. Its accelerated expansion speaks of dark energy. Its gravitational footprint maps dark matter. The solitary galaxies inside tell the story of cosmic nurture versus nature. The void ties them together, and this teaches a deeper truth. Emptiness and structure are not opposites, they're two sides of the same cosmic coin, born from the same primordial whispers. Shaped by the same forces across time, one cannot exist without the other. The glittering filaments define the borders of the dark deserts, and the deserts define the filaments. To understand the universe, you have to account for both, the brilliant cities of light and the profound, silent spaces in between. The story is written not only in the stars, but in the vast and eloquent spaces between them. We ended up looking at cosmic deserts, and it started with the Boötes Void, this huge hole in the universe. It was so big it was hard to believe, but these empty places, they're not errors. They're a basic part of the cosmic web. They came from the smallest ripples in the very early universe. Then gravity shaped them, and dark energy pushed them to expand faster. They become these natural labs where we can test physics. They hold the loneliest galaxies. They hide missing matter, they leave a mark on the oldest light. The thing is, emptiness isn't passive, it's a dynamic force. These voids are active. They carve out the structure of everything, they funnel material toward the bright filaments, they guide the universe's long-term fate. The scale is humbling. Our vibrant galactic neighborhood is the rare exception. The cosmos is mostly vast, serene emptiness. Every puzzle we solve about voids, like their dark matter halos or their accelerating growth, it leads to new puzzles. Deeper ones. This frontier of nothingness will captivate us for a long time.